So we are now ready to go to Bitcoin basics, and I think the important point about Bitcoin is that it has been a very prominent birth certificate. Yeah, and there was one paper published on October 31st in 2008, which was named Bitcoin, a peer-to-peer electronic cash system. Yeah, and it has an author. It's called Satoshi Nakamoto. And it's unclear whether it's a man, a woman, a team of people, or a state agency. So there are a lot of, let's say, detective stories around who could this be. So and the idea is that it was also implemented, this system. This was more or less like a design sketch to say how could we build a peer-to-peer electronic cash system? How do we implement a currency in a peer-to-peer, not in a centralized way? So I think the idea was not that Bitcoin was invented because in 2008 there was this financial crisis. Yeah, 2020 is the year of the Corona crisis. 2008 is the year for the Bitcoin crisis, of the financial crisis, worldwide financial crisis. Instead of this, these were independent developments. But once you have a lot of distrust in the established financial instruments and systems, there's a certain, let's say, willingness and awareness to look at new ideas how this could be achieved. And I think that is not to be neglected effect of the public perception of Bitcoin, that it provides an alternative, maybe better post-financial crisis system. So therefore, the Bitcoin has a long history. So Bitcoin has been mined very early. So even, let's say, long before 2013. In 2000, so the first Bitcoin block was mined in January 2009. So 2009 is the birth date here. And then you see more or less, in this case, the price for Bitcoins. Yeah, what was the price for Bitcoin here on an, I think this is an exponential scale. No, it's not an exponential scale. So you see the price was relatively stable. And then there was this big peak when everybody was talking about Bitcoin in 2018, and followed by a big crash again, down to the level we are right now, so that the price is here. Actually, I didn't follow the development, but it's very, yeah, it's $9,000, Uli says. So he seems to be invested still. So that you want to see that's a high volatility, like we also see it in the stock exchange prices today. What you also see here is what is typical for a currency is the market capitalization. Yeah, let's say how much money is more or less the turnover, more or less. Here we have the price line, and then we see the trading volume here, more or less. Let's say how much trading volume is existing. And again, all this data you can check it here using these public information services. It's different from, because it's all transparent and for free, this information. You don't have to have a Bloomberg account or get time-delayed information, so you get live information for free for all of these digital currencies. Okay, so therefore it has a long history, and also, let's say, the typical hype of inflated expectations, and now hopefully the valley of productivity, more or less here, plateau of productivity. So what are the key properties we've already mentioned? So therefore I can be quick here. It has this idea of trust-free or limited trust, trust into a consortium instead of trust into a single person or institution. It's tamper-proof, as we have a little bit sketched with the cryptographic mechanisms, and we go into more details later. And it has also this property, which some people think is very good, or some people say it's bad, that you have full transparency, more or less, of the money flow and asset assignments. In Germany, it's very, let's say, in the US, everybody's talking about how many houses he owns, how expensive the houses are, how much money he owns. That's more or less the typical way of saying you made it in the US, and you want to be in the Forbes list, and you say how much billions of euros you own. In Germany, I think it's sometimes very considered bad to talk about money and how much you own, how many houses you own, how expensive they are. So therefore, transparency is good. Yeah, you know, Transparency International is all about transparency of the government, transparency of the behavior of institutions. So therefore, it's good. But transparency regarding private information is often not so good. Therefore, there's a tendency, a tension that the financial system often is hidden, and you have to explicitly declare your money if you cross the border with money. And here it's inherently transparent. You would always see that things flow from one wallet to the other. Okay, now since we know, or I think we are ready now for these basic slides. So that's more or less the famous Bitcoin blockchain. Yeah? And as the name indicates, it consists of blocks, as we have discussed last week about hashed data structures. You have these blocks, and each block consists of a block header and a content, more or less, the block content. And the block content itself is an ordered sequence of transactions. Yeah? What happened after one another. And these transactions are encoded here. And the block header has metadata. Each block has a block identity, a block number, which is numbered sequentially here 100,950, 100,951, 100,952. And you have then again in the second block, so that's a so-called genesis block. It doesn't have a predecessor. No, that's not a genesis block because it's a higher number, but there's a block number 1 or block number 0, which is called the genesis block, which contains no predecessor, so therefore the pointer to the previous block doesn't exist. Otherwise, the block header contains always a hash of the previous block, which more or less is the hash value of the previous block. And so we have this hash value stored here. Then you have a timestamp, which indicates not only the number, the logical number when it has been created, but the time when the machine more or less assigned a timestamp to this block here, let's say a global time clock, more or less. So therefore also there is a certain discrete timestamps in a blockchain, that you not only know that something happened before something else, but you also can correlate it to a time, increasingly time series in the blockchain. You also have other things we will come back to later, the hash of the Merkle root, which more or less allows to have the hash values of the transactions and do an efficient search for certain transactions, and additional meta information or block information which is stored here, which we'll come to later. So therefore we build now up this chain of this block, then the next block, then hash value, which creates this, and therefore the consistency and integrity of the whole blockchain is then secured by the hash value of the last block. Okay, so far so good. I think that should be clear. Now we do a closer look into the Bitcoin header structure. Again, the header structure of Bitcoin has evolved over time. This is also an interesting detail you should consider because, maybe going back. So the important point is that this is a history of transactions. So here, for example, we don't store wallet, the accounts, the money you have in your accounts, but it's only transactions. Let's say Alice moved something to some other person, etc. So these transactions are stored here. So therefore, if you want to recover the current state of affairs, you have to take, for example, the whole history of all transactions to find out, based from this initial state at the genesis block, what's the current status of affairs. Yeah? So because these transactions are mutation operations, like add something to an account, create an account, move something to another account, etc. Yeah? So therefore, this is a transaction history like at a notary. And to find out the current situation, you have to go over the whole history here to recover the final state based from the initial state. Which has the interesting implication, if you do this for 50 years, you have a very long chain, and therefore it's very likely that maybe the ideas change what you want to store in these blocks. And that's also a typical thing in persistent data structures and databases and file systems, that you now store version information with each block. So therefore the header of the block contains not only the block size, how large the whole block is, because also this you might want to change in the future, or you want to have variable block sizes. But you also want to have a version number which identifies which software version was created or protocol version was used to define the layout, more or less, of this header. It's like an XML file that in the header of XML files you always have some metadata which tells you which XML schema has been used for encoding this XML file. And similarly, each Bitcoin, if it is decently developed, has a version identifier in each block so that you can find out which software version has been used to create it, which also allows you to change the semantics of the layout of these fields, the layout and the semantics of these fields. Okay. So therefore, this is some additional information, the block size and the version. We also talked about the hash of the previous block header and the hash of the Merkle root. So then you have also the timestamp stored here, the difficulty that has been used for the mining puzzle. We will come to this later. Nonce value, this is something like a salted hash, a salt. It's a randomly generated value which is also used for the proof of work puzzle, which will be stored here. So therefore the difficulty and nonce value together define this mining puzzle, and they are stored both here. And then you have a transaction counter, which more or less indicates how many transactions are being stored in this block. So we cover this, this is used for the consensus mechanism, and the block hash are joining for the version until the nonce field. Okay. Okay, so also the height of the block is stored in the coin-based transaction. Again, the first transaction in this block is called a coin-based transaction because it contains the fees essentially that you have to pay for mining a block. So if you want to have a block mined, you have to give the miner some fee, and the transaction to transfer the money to the miner is stored here in this first block, which also contains the height of the block. You remember the height is this value 100,952. This is not stored is also stored here in the height field, and which is hidden more or less in this TX0 transaction. Okay, so I think that will become also clearer later on if you mention it. But it's as usual, if you have data structures and algorithms, one often starts with the data structure and then talks about the algorithms, let's say the Merkle root algorithm and the consensus algorithm. Okay, yeah, so therefore the Genesis block is the block which doesn't have a predecessor, and the Bitcoin's Genesis block, we can look at it. If you click on these links here, you can more or less go to this Genesis block. And if you go to the Genesis block, maybe I can do this now. Come on. So that's more or less the initial block, more or less, which is more or less stored in the blockchain. So these are all the fields we will discuss later, and therefore you can see more or less is block 0, the depth of block 0 in the blockchain. It has been created on the 3rd of January 1915, and it contains only one transaction with a difficulty of 1, the Merkle tree root, etc. So these are these information, and then you can more or less go into it. You can see what was the transaction fee that has been paid, and what was the hash value of this. So that's more or less the amount that has been transferred of 50 Bitcoins, which is an enormous amount, but at that time it was just a toy. Okay, so the first binding, and again, the algorithm doesn't allow to spend these 50 Bitcoins, which is also a funny thing. It could be a bug or a feature. So what is the content now of this transaction? And the interesting point is, so that if you look at the binary dump of the data of this block, you will see it contains typical not random data, coded binary numbers, whatever. But then it contains some strings. The times, 3rd of January, Chancellor on brink of second bailout of the banks. So this more or less the title page of the Times. If you go at the Times on the 3rd of, where is it now, March? Oh, that's temperature. Here, Saturday, January, 3rd of January. You see this the title page here. Yeah. And you might wonder, why is this necessary? Maybe does anybody have an idea why Satoshi or whoever did this added this string to this block? You can use tweetback. So the question is, why should anybody have the idea to put a newspaper headline into a blog?
There are many answers coming in.
Okay. What's the favorite answer?
We can go through them. 1 second. The first one is so that it can be verified by everyone. Prove the date of the Genesis block, and to prove that it really is from that time, and you don't know it in the future. For date, maybe he added it to prove the first mining was there, to show that it could not have occurred before that date. So I think the last answer is actually there. So many questions.
Exactly.
Yeah.
So the idea, so once this headline has appeared, so the board decided to do this, the editorial board. So it could have been created any date after the 3rd of January 2009. Because since then it's known, what's the name. So therefore you can not prove the exact date, but you can prove it didn't exist. It was not clear what the title would be at that date. There's another theory which says, okay, it has a semantics list string. Chancellor of brink of second bailout for banks. It's all tied to the banking system. So that's more or less this coincidence that now is now Bitcoin, which talks about an alternative currency, and here's somebody talking about the second bailout for banks. Let's say the citizens had to pay a lot of money to save the banks. The taxpayer did this. Maybe that could also be seen as a critical remark. But again, nobody knows what was the real reason for that. But I think most likely, it has the goal to say that this block has not been created before that date. You never know. Okay, but again, that makes Bitcoin history a little bit interesting, all this mystery here. So that was more or less the data structure. Now we want to talk about how.
Because we got some questions regarding the data structure. Maybe we can go over them so that everyone has the chance to ask questions.
But I could also imagine that it makes sense that I first explain a little bit more what is being done with the data structure. It's simply like if you have a tree, it's nice to see the tree, but then there might be some data in the tree you don't understand. But once you talk about tree balancing and tree rotation and tree mirroring, then you better understand why this data is in there. That would be my proposal, that you remember your questions and raise it again once I explain how we work with the blockchain. That would be so that we have data structure and algorithms are always tied together. So therefore, I have to talk about the algorithms to explain the data structure.
So if you have questions, please resubmit them on tweetback so that I can ask them after the transactions in Bitcoin section here.
Okay. So again, now what I want to explain now that we understood the setup of Bitcoin blockchain, we want to talk about transactions Bitcoin. And essentially, there are two kinds of doing accounting. or doing a ledger, if I'm banking. So one is an account-based ledger where you say, okay, you have an Excel spreadsheet and it contains all names of your clients, and then you say client A has $50, client B has $100, client C has $50, etc. You know the idea. It's account-based. You have accounts, and for each account, you know how much money is on this account. This is a typical way what you would do. The benefit of the account-based ledger is it's very easy to find out what's the current wealth of a person, which is important if you transfer money. You want to check how much money is on that account. So if you, because you don't want to give somebody credit, only existing money should be passed around. So therefore, it's important how much money is on that account. Another approach is, which is the transaction-based ledger, that you say, no, I don't store the accounts, I store the history of transformations. Let's say Peter got money from his employer and he spent this money to his family. So that would be the flow of you store flow change information. Where does the money come from and where does the money go? And if you do the difference between the money you received and the money you gave away, you can compute the current status of affairs. The benefit of the transaction-based ledger is that you also know the whole history of changes. You know the origin of the money. Does it come from the central bank? Ultimately, it will come from the central bank or from mining activities in the blockchain. But you also can see where does the data flow. Are there circular schemes? The cum-ex work that you more or less can follow the evolution more or less of your money over time, so that you're full transparent not about the current state affairs, but about the whole history of who owned how much money 10 years ago. And that's, I think, a very nice approach, which is also the basis for all temporal databases, that you keep a history of all changes, and you also can replay the history forward to get arbitrary states in the history. And you also can verify properties of these changes, that changes may not exceed a certain number, etc. So therefore, a transaction-based ledger has the benefit that it's easier to keep track of the history. Account-based is more efficient to find the current state. So therefore, what we will see is that most Bitcoin blockchain systems, not most, the purely account-based, so the pure coin-based systems, they mostly use a combination of transaction-based ledger and account-based bookkeeping in main memory. Let's go through this. Here, this is an account-based system that you more or less have Alice, Bob, and Carol. They have now, at a certain point in time, has Alice 25 coins, Bob has 0 coins, Carol 0 coins, and now there's a transfer of 17 coins from Alice to Bob, signed by Alice. So Alice says, okay, I want to transfer 17 coins to Bob, which is feasible because Alice has more than at least 17 coins. So therefore, after the transaction completed successfully, Alice only has 8 remaining coins, Bob has 17 coins, the account of Carol is unchanged. Then there could be a transfer of 8 coins from Bob to Carol. So 8 coins from Bob to Carol would lead 8 coins to Carol. A decrease of 8 coins from Bob leads to this account, and you continue this, and then later on you might have a transfer from 15 coins from Alice to Bob, but at that point Alice only has 13 coins, therefore she would have a negative value. And typically big Bitcoin currencies don't allow for negative values, so therefore this would be not an acceptable transaction. Okay. So therefore, this is more or less the world state or the account-based view, and this is the transaction perspective, which contains the linear history of these transfers. And obviously, it's important that this is a full sequential history, because only then you can validate the current account status. Okay, the transaction-based ledger of Bitcoin looks as follows. That you more or less have, okay, now, sorry, we were talking about transactions. So have these transactions, so they contain certain information. And this information is visually described in the following as follows, so that you more or less have transactions in Bitcoin And the idea of these transactions is not only that you can transfer one amount, so you have one amount, let's say from Alice, you want to transfer money from Alice to Bob. Therefore, you want to transfer 5 coins from Alice and these 5 coins to Bob. That's what you want to achieve. Then you would only have one input and one output. There's a generalization done by Bitcoin, and the idea is that you want to have a transaction, an atomic transaction that does several things at once. It should not only take money from Bob and give it from Alice and give it to Bob, but also maybe money from Alice, let's say other money from Alice should go to a miner, or money should be split. Yeah, this money from Alice should be taken and go out to Bob and Charlie. Yeah, so the idea is you have an arbitrary number of inputs and the arbitrary number of outputs. It's generalizing the idea of a money transfer, that it's more or less that it has a sum of inputs and it has a sum of outputs and some mining fee. Yeah, that's more or less a transaction in Bitcoin. It has been generalized that you have input values or input transaction values and output transaction values. Yeah? And the important point is now that you form chains of this. I'm sorry. There's an animation. I thought there's an animation. So typically the input of one transaction, the output of a given transaction will then be the input of another transaction. So imagine now, maybe I do this. Sorry. Or maybe we have some pictures later on. No. What will become important is that later on we will have such a situation that the idea of Bitcoin is that you now take coins, more or less values here, you produce an output, let's say the green output, and then you use this output again as an input to later transaction. Yeah, so therefore you create now a stream of active coins somehow. Yeah, so that more or less they are called unspent output. Yeah, so the output is not spent, and this output would be spent because it has been used as input for another transaction. Yeah, so therefore the idea is now that this bookkeeping is that you now materialize this transaction or visualize them like this. You store this information. Where does the money come from? And where does it come from? And where should it go? And these can be arbitrary streams out and in. And once you created money, it's called unspent transaction output. And you can only use unspent transaction output for a new transaction. Yeah, because you want to avoid a situation. Maybe I remove this here. You want to avoid a situation that now other transaction comes. Oh, sorry. That is now here. Sorry. I have to copy it. So you want to avoid that now somebody else is spending the money for this other transaction here. Yeah, so that you have a second transaction now. PowerPoint is not stable. Okay. Let's do hope that I don't kill PowerPoint right now. So that the same transaction now tries to use the same output for the one purpose. Yeah? So therefore the idea is by having this explicit storage of these transactions, you now can trace more or less the money flow. Yeah? You see where does the money flow come from. Then you create unspent transaction output, and the unspent transaction output can only be fully consumed by one other transaction, but not by other transactions. Yeah? So therefore, if you want to split money, you have to create a transaction which takes now the money here and creates 2 smaller coins. If you want to keep something like change money, yeah? That's the idea. In addition, each transaction has a unique transaction identifier in the system, which is stored here also in the transaction, which also allows more or less to do some reasoning about the transaction number 5, transaction 500, etc. Yeah? So therefore, this is the way how to identify transactions. If you can identify the transaction, you can then identify also the inputs relative to the transaction. If this is, for example, transaction 2, this would be the transaction input 1 of transaction 2, and this would be transaction input 2 of transaction 2. And similarly, this would be transaction output 1 of transaction output 1 of transaction 2, transaction output 2 of transaction 2. Now that's what is the way these transaction-based ledgers work. Okay. There are also special transactions where new coins are created. This is something like central banks, which create new coins of thin air. So therefore, they don't have a transaction input, and they simply produce a transaction output. Okay, you could also imagine having burning transactions. A burn transaction more or less takes money and doesn't spend it. Yeah. So, but usually people don't like to burn money. But sometimes you want to burn money if you have two transaction-based systems, and in one system you want to destroy the money, and then atomically create the same money in another Bitcoin-based system. Yeah. So therefore, that you more or less then make sure that also across chains, money is not inflated somehow. Yeah. Okay. We now can. So that was my the abstract idea which I used to visualize this. Yeah. This is, I think, how you would explain it to people. Now, if we want to look more closely how this is encoded technically, we now use this numbering scheme here to write down the transactions. So therefore, we have now transaction 0, which has a transaction an empty set of transaction input. It has no transaction input, and it produces a transaction output of 25 coins to Alice. And you have another transaction which takes as transaction input the transaction 0 and the output 0 of the first transaction. Of the transaction 0, yeah, that's transaction 0, and I want to take the output of, so the green one, I want to refer to this value, and in order to refer to this green value, I say, this green value is in transaction 0, and it's the first output at position 0. So therefore, I would refer to this unspent transaction output by saying this is 0. Then I would create an output, which is now 17. And I want to give it to Bob, and I have a transaction output 2, which goes with this blue, which should go 8 coins to Alice, and this is signed by Alice. So therefore, the next transaction could now come and say, I want to refer to the transaction output of transaction 1, and at position 0, that would be the yellow input, and a later transaction could refer to the second output by saying, I want to take from transaction 1 the second output at position 1. Yeah, and that's the way I can refer always in the inputs to existing transactions, and then I can define the output which I'm generating, and also the person to which I want to spend the money. Okay, I think that should be clear. So Alice also sent money back to herself. Maybe we should talk about this. So here, so Alice now sends 8 coins to herself. Maybe can somebody explain why this is the case? Uli, are there answers?
I'll set up the question on Tweetback so you can answer below my question, and we gather some infos. Why does Alice send money back to herself?
In transaction 1.
In transaction 1. So there are 3 answers already. First answer is it's leftover money. Then the other one is in order to not reuse an address. So good thinking there, but it's the same address in here, in this example. Because all the value has to be consumed.
Yeah, that's the idea. So the idea is all 3 so the first and the third answer are the correct ones. Yeah. So also the third one might be correct if it would be a different account. So the idea, the rule is if you consume this money, you have to consume it fully. So therefore, you have to now take 25 as input. And since you don't want to burn money, you better pay back the €70 to Bob, but then you split the amount that you create now the unspent transaction output, which is 8, and it should be under your own, let's say, regime. Yeah? So therefore, Alice sends the money, the change back to herself, more or less. Or to a newly created, that would be the answer 2 you gave, to a newly created Alice account, which she can then use for further transactions. Okay. Again, and that could be the case that now Alice spends a lot of money and has a lot of change back. Then again, you could more or less take from different accounts your money and put it back to one of your accounts. Yeah. So therefore, there you can now create arbitrary forking and merging streams of money. And again, what we will see later, we now always talk about money. And one idea, obviously, is the money could be other assets, like the ownership of cars, or the right to use energy, or the voting rights in a company. So therefore, you could accumulate voting rights, you can split voting rights, you can split shares, you can move shares. Yeah, so that's the idea. And again, the same thinking would hold, that it's much smarter to keep track of all the transactions versus having only a register of the current usage. Which is interesting, by the way, if you talk about the law. For example, in Germany, we have registers which are state-owned. For example, registers of cars or registers of land. And the land register in Germany has the fact that the truth is not the reality, but what is written in the register. Yeah, so therefore, the ownership of land is not documented by past transaction history, that the king 500 years gave this person the land, and they then gave the land to their nephews and to their children, and so on. You don't take the history of all transactions to prove that you are the owner, coming from the land taken by your predecessors, but you go to the notary, and the truth is in the register. In France, it's different. There you still have this idea that you have to go back to the kings, so therefore they keep a long history which roots back to the kings. If you can create documents in the past that show this, then you have to rewrite more or less the reality. I think it's a nice also anecdote which I learned talking to lawyers. Okay, so this is now the idea how you would do this transfer in a centralized data structure, because up to now all this information was stored in one. So we had this. This one chain. Now we talk about that this chain doesn't exist only once, but it exists multiple times, and that we have a consensus to compare the different versions at different locations. And that will be the main topic of. Yeah.
Okay. So first, let's answer the questions about the previous sections and then continue with the Bitcoin network. So first of all, regarding the Genesis block, why can those 50 Bitcoins never be spent? Is the binding reward not accessible by the miner of the initial block? Could you please elaborate on this?
Yeah, I think it's not very important. It's written here. The fact it cannot be spent is based on the source code of the current Bitcoin core client. Yeah. So the core has a bug or a feature. I don't know. I would think it's a bug. You know, typically the boundary case is spending block 0. Somebody maybe didn't think so far. So therefore, it could be a bug or a feature that the code itself doesn't allow this. Yeah. And
so it's actually documented in the source code. If you click on the link below, so you don't have to do this. You can do this privately on your own. It's actually documented in there that the block 0 is not included into the memory pool or into the state. So you see here special case for the Genesis block, skipping connection of its transactions. So, but no one knows the reason why that is.
Yeah, and again, it's Uli likes such stories, because it's insider knowledge. Let's say, how would you say it? It proves that you are a very cool expert in this area, but I think it's not really relevant for. It's just anecdotal knowledge.
Yeah. One question: how does it make sure that the new block refers to the current balance of the sender? Could there be transactions between the new one and the one that the new block is referring to, leading to a user spending more than she or he has?
No, I think good question. I think what's very important if you know databases. Yeah, you know, in databases you typically have concurrency control issues. Yeah, so let's say somebody, you have this idea. You have let's say, imagine you have a apartment where different people live together, and you check in the refrigerator how many bottles are there. Yeah, and then one person wants to do a party and says, okay, there are 5 bottles. That's enough for me. Yeah, in the morning he looks in the refrigerator, says 5 bottles are in there, and I can spend 5 bottles for my party. And maybe the other also appear in the roommate does another party, and he wants to spend 4 bottles. Yeah, he checks the bottles, he says they are there, invites the people, but then one of them comes first and takes it out. Yeah? So therefore, this interleaving of checking the value that is there and spending the money has to be atomic. Yeah, so therefore, it's very crucial that this transfer here is done all or nothing. Yeah, so the asset properties of transactions are done here, that in atomic fashion, this money is taken and atomically created. And either this transaction fails, it goes through, then this is done, all of them are done, or none of them is done. So that's the atomicity of these transactions, this all or nothing principle. And therefore, it's important also that this is possible in Bitcoin. So therefore, the checking of the availability of the funds and the spending of the funds is done atomically and not in different read and write operations, which happen sequentially, because then you could have an interleaving of them. The second thing which is important also, that it's a chain. It's not a branching, it's not a direct acyclic graph or even a tree that you more or less can have more or less unspent transaction output, which is parallel spent in 2 directions, but all these transactions are done sequentially. Yeah? And that's also very important, like in a serialized fashion in a classical database. Yeah? So therefore, the asset properties, atomic, consistency preserving, here the consistency is checked, yeah, that the money is there. Asset integrity concurrency control, integrity preserved and durable. That is also what you get now in this scheme, what you expect from classical databases. Okay?
Yes. Let's continue with the next question. What is meant exactly by burning money? Is the burned money lost?
Yeah, exactly. So the idea is if you more or less take 50 coins in and you don't produce a transaction output, this money is taken away, it's now spent, but it's never appears nowhere else, nobody else can access it. Yeah.
And in the same direction, if the transaction input is more than the output transaction, will the transaction in Bitcoin considered as valid? So if the input is larger than the output.
Exactly. That's so actually I didn't read the source code, I didn't try it, but I would assume it's also possible to do this. Maybe it could be a safety issue that you say either you fully burn it, but I don't know what the designer did. Yeah, but it's also, if you look at other design options from other chains, you could either say it's lost, yeah, but obviously you don't want to create money out of thin air. Yeah? That's also something you want to avoid.
Yeah, exactly. So transactions which have a larger output than the input are obviously not allowed or invalid. But with the higher input than the output, the rest is usually sent to the miner as a mining reward. But this is covered later on when we talk about mining consensus and everything. And yeah, one last question, I think. Why would you burn money if the money is spent? Why can't anybody access it anymore? So what are the reasons behind burning? Why would you do that?
Okay, so for example, one question, imagine you have a company like Apple, why would buy Apple their own stock back? So the idea, if you have a company and you buy stock back, you reduce the amount of available stock. Why does Apple do this? And why everybody hates them for this?
Do you want to ask that the audience?
Yeah, it's a question. That's a question for the audience. So many big companies which have a lot of cash, they use their own cash to buy their own stock. What's the purpose of that? Or you have a central bank. Why would the central bank burn money?
So it's on Tweetback, you can answer below my post to answer that one. So the first one is already in, maintain the price balance.
Price balance?
Central bank stupid Apple to raise the share price, drive share prices
Exactly.
up, less supply,
Exactly.
higher
So
price.
let's talk about the share prices. I think the idea of the share prices is obviously you have a management, and the management models it gets paid by the stock price. And the easiest way to manipulate the stock price is to buy your own stock, yeah, which is, I think, ethically very wrong, but it's heavily done. Yeah? So therefore you have the owners of the company, and the management buys their own stock or stock option plans and or reduces the stock option plans to increase the share price, which is a very bad behavior, but it happens a lot. Yeah? It makes Bezos and his friends sorry, Bezos is unhappy, but if he would have a manager that does it, and Apple is not is a stock-owned option thingy, stock is publicly traded. That's a thing that the Apple managers most can increase the price of the stock prices and manipulate them. And the central bank is the same idea, that more or less by inflating money or reducing money, you also can have an effect on the what's it called, Kaufkraft, on the not the Kaufkraft, on the amount of money available, and you create scarcity of money or you create cheap money, yeah? And therefore you can manipulate the exchange rates with other countries.
Yes.
And the value of money,
okay,
with tangible goods. Okay.
One last question, I think, to the previous slides, because some people had also questions to the data structure, and I think that's quite a good question. There is a field in the header which stores the hash of the previous block header. So if you would go one slide, I think slide 7, is it? Then why does it not store the hash of the entire block instead? If it stores the hash of the previous block header, then how are the header and the rest of the block linked?
A good question. So we have also the hash of the Merkle root in it. So the hash of the Merkle root more or less secures the transaction part. Yeah. So here the hash of the Merkle root is the hash value of the body. So therefore the header contains the hash of the body. Yeah. And therefore, if you have a hash of the previous block header, you also have implicitly a hash of the Merkle root of the previous block. So therefore, it also secures the previous block.
Yeah, exactly. So due to the hash of the Merkle root, which is included in the header, it's not linked directly, but indirectly. Yeah. Okay. I think there are no further questions anymore, and we can continue.
Okay. Okay, so we now are ready. We understood, let's say, what's the idea? How do we want to, what's the algorithm for checking the ledger? What's the algorithm for checking the balances? And what's the algorithm to maintain integrity, more or less, in this data structure? In the assumption it's one data structure. But now we talk about the Bitcoin network, and the Bitcoin network has the idea, oops, what's happening? Sorry, I'm on the wrong page. So the Bitcoin network, you have to imagine like this. So the Bitcoin network consists of a lot of nodes, which keep a copy of the blockchain. Yeah? So therefore here we have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say 80 nodes or 50 nodes. So we have 50 copies more or less of blockchains. And the hope is that all these 50 copies are the same. Yeah, that's the idea. We want to have a peer-to-peer networks. All these nodes have the same, are peers. There's no central node, and it has a very random topology. So it's a mesh network that more or less some nodes have, let's say, 1, 2, 3, 4, 5 neighbors. Here are some nodes which have only 2 neighbors. So therefore, we have a more or less a connected network of which is the Bitcoin network. It consists of nodes, and each node contains a copy. A full copy of the whole blockchain. That's the basic idea here. So therefore you have 3 kinds of users. You have so-called or participants, because these full nodes are actually run by people. This is a node maybe that runs on your laptop, this is a node that runs in China, and this is a laptop which runs maybe in US. Yeah? And they also have some peers with which they exchange information, and then the information is propagated through the network with hops, like the IP, the internet. Yeah? The internet consists also of nodes which have a limited number of neighbors and then have a topology which is rather flexible. The important point is a decentralized fashion. It's not something like a master-slave architecture that you have one central node and a tree of slaves, but they are all equal rights. So you have now these full nodes. Then there are so-called light nodes, and light nodes only keep that part of a blockchain which is relevant to your own accounts. That was an early idea that, let's say, your laptop doesn't have to store the whole Bitcoin, but maybe only transactions which affect your own ownership. Yeah, so they'd be more or less synchronized with the rest of the network, but they only keep track of the blocks and the transactions that are relevant for you. They are called light nodes. Currently, I think they're no longer used in practice. You could run nodes as light nodes, but that's practically not done. And then you have a third role, which are the wallet owners, which are outside. Yeah? So these are more or less the infrastructure people, which run the infrastructure, let's say in this case 50 nodes. But you could have millions of users using these 50 nodes, and these millions of users would trust that these 50 nodes make sure that the other nodes don't cheat. That's the basic idea, that you have a set of miners which running the nodes and a set of users with wallet owners which use the network. So therefore, in order to communicate with each other, they have to find first each other. There has to be a bootstrapping process. If you create a new node, it has to somehow find the network. And so therefore, there are standard ways, more or less, of starting addresses from which you can now look for neighboring nodes and can attach yourself to the network. The second one is important. You want to synchronize your blockchain. So therefore, if you have changes on a neighboring node, they should propagate the changes to you, which is also another reason why you send transactions as data structures, because these transactions or transaction blocks are propagated here through the network. So therefore, you want to synchronize the blockchain. Yeah, let's say if you join the network, you would say, please give me now all the whole history of the blockchain network so that I can become a full node. That would be syncing. Then I have sending and receiving transactions that I can now send transactions to the network, and I can receive transactions from the network, and I can send and retrieve blocks from neighboring nodes. Yeah. And so therefore, such protocols which propagated from neighbor to neighbor and not in a directed fashion is called a gossip protocol. So therefore, messages are view blocked or transactions are validated and then broadcasted. Yeah. So the idea is that if a node gets messages, each node verifies these messages. It's not like simply broadcast them to everybody else, but it first validates whether the transactions in this block are valid, yeah, whether they don't create money out of thin air, and whether they are signed by the respective owners, and the amount of money is available. These checks are done for each transactions when they are propagated. Exactly. And then it also keeps track which nodes it already propagated, so that more or less nodes are not sent in circles around. So therefore, after a while, these sent nodes are sent over the network and are propagated in the network. Okay. Yeah, let's talk about these individual points, how this is done. So that's more or less what the gossip protocol does. The gossip protocol propagates this kind of information and allows to attach to the network. So to start now a new network, you can look at IRC channels. Yeah, you could go to social media, the internet relay chat channels, and you get now addresses of new clients. Yeah. Another way is hard-coded DNS services in the code. Yeah, you download the code for a node, and if you start it, it contains some well-known DNS services which offer the IP addresses of nodes. Now, there are some trusted nodes, in this case, DNS services, which you can now use to look up certain names through the DNS protocol. which might be a attack point if the DNS server would be faked. Another idea is that you have hard-coded seed addresses, which are IP addresses of machines that are known to exist. Yeah, some seed nodes, and based on these seed nodes, you can always find more or less the one and only Bitcoin network. Alternatively, you could also provide new addresses here. For example, if you want to create a test network, etc. You could also say, now I want to join a different network, which is partitioned from the initial one. And you could also provide text files to provide these addresses. Okay, so that's more or less the way how this network stays connected, more or less, and established itself. We already talked about the roles in the Bitcoin network. I think I don't have to say so much anymore. But let's walk through it. It's a repetition. Let's first come from the consumer side of the network, or the user side. These are the wallet owners. They own different private keys to unspent transaction outputs. These unspent UTXO is the abbreviation. That's more or less the private keys to these unspent transaction outputs, because they are signed that this should be spent by them. He or she is the owner of all stored currencies on these addresses. He or she can send money by signing and publishing new transactions to a connected light node, full node, or miner. Yeah? So therefore, what I would do now, if I'm a volunteer, I would connect to any of these nodes in my neighborhood, and then would sign my message and send the transaction to this node, and this node would validate this transaction, and if it's valid, it would propagate it, and sooner or later it would arrive also at that node. So that's the basic idea, how in a globally distributed network these transactions flow through the network. So the full nodes then maintain the complete blockchain. Its record of the chain is it has a complete record of the chain. It was difficult to read, and it contains every single transaction and block until the genesis block. Therefore, it's called a full node because it has a full history. And it's connected to other full node and exchanges information, namely validating each transaction it receives and relaying all validated transactions and blocks to other, relaying all new transactions and validated blocks to neighboring full nodes. Okay, light node I already mentioned. It's looking whether a single transaction of the wallet owner was executed correctly. So therefore, the purpose of the light node is that you run the light node, which connects to the network and makes sure that your transactions have been validated and moved to correctly added to the network. This allows you to, more or less, if this is your light node, to observe the behavior of the other nodes, and you get notified once the consensus protocol reached consensus about your transaction, and that you can then, based on this information, be sure that your transaction is durably stored in the blockchain. That's the light node. And again, as I said, it's almost no relevance in practice today. Typically, you use centralized services like exchanges or centralized servers, which you can attach, you connect to. So what's now the miner? The miner is the person or organization that runs such a node, and the miner gets now a benefit for doing this. It's like a bank, bank is not a charity, so therefore typically banks require fees. And there are two kinds of fees you could have. One fee could be that you own money. That would be more or less a management fee, that the bank has so much money for you, and maybe you have to even pay taxes on that, or some negative, or you get either a reward for owning the money from the bank, or you get more or less, you have to have a Verwahrgebühr, you have to pay a fee for owning money. But typically, money in rest doesn't cost any money. So therefore, typically what banks do, they ask money for each transaction. If you transfer money, let's say, for example, you know this, if some of you sent money back with Western Union to your home country, they have rip-off prices, how much money you have to pay to transfer German money to foreign currencies. So therefore, typically, the miners earn money by the transfer. If you want to transfer money, you not only give a transaction to the network, but you say, I'm willing to pay so much money for this transaction. Yeah, so therefore it's a bidding process that you say, I want to spend this money, but occasionally I want to give, let's say, 20 cents to the miner, or I want to spend 0.5 Bitcoin, and I want to pay 0.1 fee. I'm willing to pay this fee to the miner that adds this to the network. And therefore, you can now, by giving, you have more or less a dynamic pricing machine, because you have now offers of transactions which are willing to spend money, and then there's a pool of miner, and the miners can decide whether they accept this offer, because currently they don't have nothing to do, and better than earning no money is earning a little money. And if a lot of people at the same time want to spend now, get their transaction to the network, they would try to give more mining fee, so that there's a competition between the miners to take your high transaction with a high commission fee that is added early on to the network. Yeah, imagine the price of Bitcoin is dropping rapidly and you want to get out of Bitcoin, then you are willing to pay a lot of money to get quickly out of the Bitcoin before the price goes down even quicker. Or if the Bitcoin is rising rapidly, you want to pay a lot of money that you now get this low price before it goes up. Yeah? And that's almost the game theoretic way of motivating miners to run the network, because they get transaction fees for people running on the network. There could be also a disaster that nobody is using the network anymore, like with the airlines. Yeah, all the planes are down, and the airlines earn money by flying planes. So therefore, also the blockchain network somehow could go bankrupt or go out of business. That no one uses the network anymore. It dies more or less out of obsolescence. But as long as people have money on the network, that's very unlikely that no transactions would happen with this money. And if there would be the danger that the network dies, people would start sending transactions to themselves to keep it alive. Introduction to Bitcoin and blockchain. And I also discussed how do transactions look like in Bitcoin and what's the difference between account-based and transaction-based ledger. I also talked about what's the Bitcoin network, that it is a peer-to-peer network with the gossip protocol, and that it has different types of nodes. Yeah, so I go quickly through this without just to get you more or less on board. Then we will talk a little bit about storing Bitcoins, because unlike a usual world where you can go to your bank and get the validation that you are you, we are living in a perfect digital world, and so therefore, if you lose your keys to your wallet, all the money is gone forever. Yeah, you see it, everybody can see it. But you cannot access the money, and this is a typical disaster that happens in all blockchain-based systems. That the management of the keys is a major issue, and so therefore we talk about this also. And then we move on to the next section, where we talk about the protocol, how you do this transfer, and what are specific ways to also attach some conditions to payments. So currently we talk about unconditional payments. Essentially, the idea is you say as the owner of the money that you want to transfer the money. Often in practice, it's not only that you do something, you pay money, but often you pay money for the exchange of something you get. For example, you pay money for that I, for example, got a sandwich from my wife, so that I can. So I get this sandwich, and she gets the money. Typically, that should be atomic swap. That you want to do two things at once. You want to get some assets or access to some information or the execution of some service. And in the exchange, you want to get the money. And normally you need notary to make this. If you want to sell your house or you want to buy a house, then there's this critical moment when both parties have to change the ownership of the house and the payment has to happen. Because nobody wants to only give the house without money and nobody wants to give money without the house. And typically you have a notary in between which does this in an atomic way so that nobody can interrupt this transfer from both parties. And now we will see later on how we can add conditions to the payment and how we use the conditions later on to enable basic transactions. And as an outlook, the ability to have conditions attached to Bitcoin transfers are limited, and therefore this gives rise to the idea of having programmable blockchains where these conditions can be more expressive than the rather limited ways you will find in Bitcoin. Okay, that was more or less the overview of what we want to achieve today. As I said, we start now what we discussed last week, that the worldview you typically have is the world state, that Alice, Bob, and Carol have a certain amount of money at a certain point in time. Time moves down here, and money transfers money, Alice transfers money, etc. And this goes on. And we want to avoid illegal world states where people spend more money than they have. So this would be an illegal world state. And that would be typically how you would do it with an Excel spreadsheet, that you make sure that these values are not changed. And that would be an account-based ledger, whereas if we have a transaction-based ledger, we would only store the list of transactions from an initial state, so the initial state of the system, where maybe Alice had 25 coins and nobody else had coins in the world. And the transaction-based ledger itself can also be visually represented, so that we don't write this simply as a sentence down, but that we more or less write something like a transaction record. It's a visual representation which consists of a list of transaction inputs, where does the money come from, and transaction outputs. And if there is more transaction inputs, let's say the amount of the transaction inputs is higher than the transaction output, the excess money goes to the miners as a transaction fee, more or less. That is the basic game rule of the game. And so therefore you now can get from multiple parties money, and you give it out to other parties here. So that's the basic idea. And you have to be able to be authorized to access that money, and you have to be authorized to access this money. And we will talk more about this authorization process in a minute. But the basic idea is that the transactions are now these multi-input, multi-output transactions, which are performed atomically. And in the transactions, you can refer these data by having the transaction ID, and for the transaction input to have the index of the number. That's index number 1, index number 2, and so on. So that you not only can reference transactions, but also parameters of transactions by this position. And this is this notation that we have the transaction ID and the transaction out number. Okay, so that was covered already last week. So then we talked about that this blockchain is not only stored on one single node of the network, but the idea is that we have a large number of copies, thousands of copies, for example, in the Bitcoin network, and that each node doesn't talk to thousands of other nodes, but to a limited number of peer nodes, which they discover, and then can receive and send messages to the neighboring nodes. And the neighboring nodes then spread the messages. So therefore, it's a gossip protocol that sooner or later, through a limited number of hops, you can reach now every other node. And the network is initialized that if you join the network, you first synchronize the state of the blockchain, then you walk through the list of the blockchain and you validate that you get a valid blockchain. You don't simply copy it, but you now make sure that all the transactions you receive from this node, if you now a new node, are consistent. You do this again. Therefore, you want to have a valid copy of the blockchain, that's not a hoax. And only if it's valid, you then start to accept messages to add nodes to the blockchain, and you then take part in this protocol to find a consensus with the other nodes. And we come to this later. Then the question is, we also covered this, how do you find the network? And there are different ways, which are listed here, how to find the Bitcoin network so that you don't have different unconnected networks which claim to be the Bitcoin network. We also talked about the roles, the people running the network, which would be the full nodes, which is a piece of software, and the miners is software which more or less runs solve the mining puzzle, and only if they can solve the mining puzzle, the miners, they can add new blocks to the full node, to their node. And these changes are then propagated to the other nodes. So therefore, we have the users of the system, which are the wallet owners. We have the full nodes, some of which participate in the mining process. Others simply keep track of the status of the blockchain. For example, you do research projects, you can now create a full node and download all the information from the blockchain. You can validate that it's true. But if you don't want to spend money for the mining, you also can use it. It's freely accessible without any cost. The light nodes are only used or can be used, but you only keep track of the transactions which are relevant to a certain wallet owner. But again, this is currently not really used because most people interact with the blockchain not directly with the blockchain, but through an exchange. And there you more or less don't have to run your own light node. If you are, let's say, bored and you not only want to play Minecraft, but you want to do Bitcoin mining, you can download it. Then you would get a file system, more or less. Here you would download the software, like, let's say, Excel or whatever. You would start it. And the data, I think, is not enormously big. I think in April it was 210 gigabytes. It's all transactions of the full history. And it grows more or less linearly over time. Yeah, so therefore it's not an exponential growth, but it's a linear growth because the transaction throughput is heavily limited in the Bitcoin blockchain. And therefore you would find essentially a directory structure where you have a folder with blocks, which contains block information as files. Then you have index information to navigate more easily through the blocks. And you have the current chain state where you know more or less some snapshots where you more or less look at, the chain state is essentially this, the current state of the chain you're computing, whereas the transaction blocks are this. Yeah? So it's a rather simple also representation. Here you don't need to have installed extra software like databases, etc. It's all included in the binary of this Bitcoin client, or Bitcoin client, which is a Bitcoin peer-to-peer client. Yeah. You also then have some metadata, a list of banned servers, fee estimates, mempool, peers, wallet data. But again, we don't want to go to the details here. That should be sufficient. That it's no magic to run such a Bitcoin node. Okay, now we want to understand how a newly created transaction. So you have now a consistent blockchain, and what needs to happen that you can add a transaction to the blockchain. Yeah, and this is essentially what typically the bank would do. Yeah, if you write a message to your bank and say, please send money to somebody else, the bank would verify whether you're allowed to do this. Yeah, and we now look in this animated graphic how transactions are included in the blocks. So in the first step, that you would write now the transaction, yeah, like a Überweisungsträger in your bank, that you write Alice should get or Bob should get so much money, and then you would sign it with your private key that you are the owner, that you are the owner of this account, and that you allow Bob to get the money. That's more or less the idea, that you create this transaction, and this transaction is a piece of data which contains both the amount you want to send, the address who should get it, and also the signature that it's you who sent this. This can then be in the next step. You send it, so that's now happening on your personal computer or in your browser, and then you send it to the next full node you're connected to. Yeah? So you send this message to the full node, and the full node now validates the transaction. Yeah? It checks whether it's correctly signed, and essentially whether it's a positive account, and maybe the message format is correct, but nothing very much needs to be checked here. But it wants to make sure that there are no denial of service attacks here. So once the signature is correct, the message is sent for the full node to its neighbors. Yeah, so with gossiping, 3 neighbors, 4 neighbors, and so therefore, this transaction is saved in the so-called memory pool. The memory pool are all transactions that all users now send to the network. Yeah, because you're not the only bank client or network client. Yeah, there are hundreds of them. And the idea is now that there are hundreds of people which want to send money to other people, and the question is who gets which transactions are being sent. The nice part here is because your transaction also includes an indication how much fee you are willing to pay. Yeah, because you have the inputs here, 5 inputs, 5 outputs, and then the difference is the transaction fee. So therefore, the miners here in the network would see, aha, this is a transaction where I can earn a lot of money, or it's a transaction where I don't have so much money. Yeah, so therefore, with giving more or less money, you can more or less give some priority to your request to say the bank, yeah, if you use mine first, you earn more money than if you use another account. Yeah, so therefore, this incentive of the variable field allows more or less to get a little bit ahead of the crowd in this memory pool. Yeah, so then the miners would take now your transaction and other transactions. They would essentially use the transactions which more or less they do a little bit of bin packing, that they add now the transaction to this block to earn as much as possible bitcoins. And then they would try to solve the mining puzzle. Yeah, so they would do some calculation of the hash values to find now the correct add on to your transaction block with their mining address to more or less solve the puzzle. And let's say thousands of miners maybe currently, or hundreds or 10,000 of miners do this concurrently. And whoever has the first mining solution then is able to add this new block with your transaction to the blockchain. Yeah. So and then the other miners now validate this result, yeah, whether it's really the correct result. And if it's the correct result, they propagate again now this transaction, this new block with the blockchain, and it's added by the others also to the blockchain. Yeah, so that's more or less the typical way. If you're now imagine you're sending your money here. It's like with the bank. Yeah, you go to the bank and you send money to somebody else. And typically at the bank, that takes days. Yeah, until, well, let's say 1 or 2 banking days. Or if it's a vacation, it may take longer, until you, more or less, the receiver really gets the money. Yeah, so here, only at that point, the receiver gets the money. In the Bitcoin system, this may take something like minutes here. Or if it's very busy and there's a lot of queues, up to 1 day in very extreme cases. Yeah? So again, this process takes time because you have to create now consensus. It has to spread through the network. And maybe there are other people which pay much more money than you want to pay. So therefore, if you now have an online banking system, that would be really puzzling because you want to more or less withdraw money or you want to send somebody else money. It takes some time, and therefore later on you have to show your users, if you build a blockchain-based system application, that now this transaction is accepted. Yeah, it's valid. You know, nobody's complaining that's invalid, but it may take time to be executed. Yeah? So therefore, that's the life cycle. What you see, that you see it has been added to the network. Okay. So I think there's one section, I don't want to go into the details. I think it's mostly important at the time when most of you had owned Bitcoin and there were some disasters that people lost their Bitcoins. So therefore, there are essentially different ways of storing Bitcoins. And again, as usual, if you have certain things, if it's all about security, there's always the factor that the more secure a solution is. Let's say if you have two-factor authentication, it's not that convenient. Yeah? So therefore, mostly people like to have very convenient access to their bank account. Yeah? Let's say if you have a credit card, you simply want to move it now in the near field communication to the point of sales and you want to pay. That's very convenient, but it has maybe the risk that if somebody gets very close to your credit card, at that moment he can steal money from you. And similar with Bitcoin storage, key storage, if you have very secure solutions, they are very inconvenient to access them. You have to more or less type on some data, you have to have a device in your hand, etc. And finally, there's this topic of availability. Let's say, more or less, if you're on the move, do you have to be at a certain location? Is it at home in a drawer, or do you have it on your mobile phone, which is also then a point of availability? So that there's no time lag between accessing the key and using the key. Okay. Obviously, the simple solution would be to have somewhere a file on your hard disk where you store your keys, because it's a rather long thing. But then the problem would be that people could steal now, get access to your hard disk, and then they could store it. So therefore, this would be then called hot storage. It's immediately available. Through some software, piece of software, and it's very convenient. And that would be the typical thing if you store it somewhere on your PC or on your mobile, maybe as part of an application or as a plain text file. Another way would be cold storage, that you more or less put it on the hard disk, but you unplug the hard disk. So if a virus encrypts your hardware, if your hard disk is crashing, or somebody steals it from your hard disk, that's a very bad idea because you cannot recover it. Yeah? So therefore you would have to have at least a backup copy of it, or what it would be better to have cold storage, that you don't keep it live on your computer, that it can be taken away, but more disconnected from the World Wide Web and from your computer. So on a memory stick or on a hard disk which you unplug. Okay, so therefore it's safer, but not that available. Another idea is that you have a brain wallet. I think the older you get, the more less reliable it is. Yeah, I'm having a lot of difficulties remembering names, but the idea is that you have something like a very long passphrase, yeah, a very long sentence, which you only remember, and which has a lot, which is very long, which you can use as a passphrase. And so therefore the idea is you have now this long passphrase and you have a function which based on your passphrase creates a private key out based on it. Yeah. And again, the problem is now there are many TV shows. If people say something, maybe I can do it also for you. Please think about a flower. Write down which flower you're thinking about. Okay, now the question is, who thought about a rose? Uli, how many roses do we have?
There are no comments right now. 1 second.
Yeah, but this is essentially what's happening. Yeah, that mostly, if you ask people about something, there are some prototypical flowers. Yeah, the rose is often the flower people think about in Germany, and the same thing, think about animals, etc. It's very interesting to see what people do. In particular, if you have some pictures, you showed previously some pictures, then most people think in the very same direction. Yeah. So therefore, I think this offline guessing or password cracking is still possible because you don't use a very random text because you want to memorize it. So therefore, they could also be found. Yeah, here, for example, this would also be a text here, yeah, which it's very hard to remember. So therefore, you would have to write it down. But if somebody writes it down, they cannot do something with it because they also would need the function to compute from this text your wallet. Another way is so-called paper wallets, where you more or less print out the key material on paper, and you get more or less a public address. So which you can show, and then you have more or less a private address, which you can leave in a secure and safe place. Yeah, and again, there are problems if there's a fire, yeah, or therefore, if you keep money at home, there are all kinds of risks. Yeah, so that maybe your wife cleans up your desk and it's all gone. Or people could more or less look at the printer where you print it out. Yeah, they give it to you, but maybe in the background they have a printer which more or less keeps a copy of what you're printing. So these are more or less side channel attacks. More secure are these hardware wallets, but again, it's more difficult for you maybe to track what is happening on these sticks in hardware. So again, they allow more or less to store information, to keep the keys, and only if you want to interact with your money. It's like these chip cards. You insert it into the computer, and then you also have buttons on it to confirm or reject transactions, yeah, which also cannot be manipulated by the PC. So that's typically something like a chip card reader. Now it's then a hardware wallet. What is typically now happening is, and the nice part here is it's totally decentralized. What's happening now since 2008, that more and more people say, oh, this is such a hassle. Isn't it more easy to, let's say, go to Bitpanda, Bitfinex, Mt. Gox, that you more or less have a website where you log in, as usual, with your password reminder, secret password, maybe email notification, SMS notification as a second validation step, or maybe even a telephone interview. If you lost something, they can ask you for your telephone number and for a picture of yourself. So there could be possible ways where you open an account at these exchanges, and these accounts are typically web accounts. Yeah? And the disadvantage is that the advantage for you is very convenient because you can log in with Google, you can log in with Facebook, you can do all the kinds of things which you are used to. But unfortunately now they have a lot of your keys. Yeah? So therefore this is a very dangerous thing that now if they use your keys and they get stolen, and in fact there have been multiple hacks against these accounts because they are very valuable target, your keys can be lost again. Yeah? So that people then get access to your keys and get stolen. Okay, but again, many banks do this. All the big banks which offer you to handle your Bitcoin accounts, they essentially have then also cryptographic hardware, etc. And they have TÜV-like procedures that people verify that they don't have, the employees don't have access to the keys. But there's still some software and some hardware on which all this depends. And therefore, you have to have trust again in these exchanges that they do what they promise to do with your keys. Okay, so that's a small excursion.
And in the meantime, maybe we can answer some questions.
Some questions, while I'm switching.
Feedback. So I got two questions here. The first question is, the memory pool is a local instance, right? So can it be that every miner has a different mempool?
The mempool doesn't have to be synchronized because they might have different copies of it, because it's only important that whatever they produce in the end, the mempool is local to each miner, and miners have interest in getting many transactions from different places, so they also propagate this because they need many input from many clients, so therefore they share it. They are self-interested to share the content of the memory pool, but it's not important that the memory pool is the same at all nodes, because only the result has then to be verified that whether it's compatible with the existing blockchain.
Exactly. A second question is, how can Bitcoin trading work if the execution of a transaction can take so long? So you mentioned 10-minute block time. How are we able to trade Bitcoins faster than that?
Yeah, that's unfortunate. So since we are the only place to trade Bitcoins, more or less. Okay, so you could more or less trade Bitcoin outside of the Bitcoin place. Like futures on Bitcoins or instruments built relative to Bitcoins. But if you want to let's buy and sell physically Bitcoins and not only options on Bitcoins and other systems which are off-chain, the only way to do this is go through the one single chain. And since the one single chain has a very limited throughput, as we will learn later on, all these other trading options are also very slow. Yeah, so therefore this trading is limited, and therefore also you can get very crisis situations. We have later examples where everybody wants to get out of the thing, and there's a huge queue building up, and everybody's paying enormous amounts of money to be the first in these queues as a transaction fee. Yeah, and so therefore it's also a very risky thing in Bitcoin to do trading, or flash trading is, I think, not a good business there.
Yeah, to add to that, so if you, for example, if you store your Bitcoins on a hardware wallet, then it's really hard to get it traded because you first have to send it to an exchange. But if your Bitcoins are already in an exchange, for example, at Bitfinex or some others, then you can trade them instantly there. So this is where the exchange only does the trades in the database, so to say. So they don't have the waiting time of 10 minutes on the Bitcoin network. So that's not for them, it's not the issue there. But obviously these websites get also overwhelmed when a lot of people want to sell or buy at the same time. So that's also always could be an issue. Okay, but apart from that, I think,
with all exchanges, also Deutsche Börse or on Vista, they had the same problem with real money. So in the Corona crisis, they were flooded by requests, the servers went down, and they didn't have the real money. It was only, let's say, also if you go to the German So there's two things. There's settlement, which is happening instantaneously, also for flash trading, and then there's clearance. And clearance is really shifting the money from one place to the other, which takes weeks sometimes. Yeah.
Yeah.